Let's take this very simple example. Let's say that we are creating here a runnable. Let's call it a writer. And what we do is we are adding in a for loop, we are adding to our map and to our list the value. So we are, for example, adding key plus whatever is the I and the value whatever is the I, and we are adding to the list item I, right? And the next step is we are creating two threads, thread 1 and 2, and we are starting two threads, and we are waiting until those threads are finished their work. So as we have seen earlier, if we have a shared resource, right here we are using two shared resource, map and the list. So earlier we have seen that example with the integer. If we are using a shared resource, so then if we are using one, two or more threads, we may have a race condition. Previously what we did is we have solved that problem with introducing a synchronized keyword. So in the synchronized keyword, so what we do is we are blocking this part of the code or this part of the code. So whatever makes sense. So only one thread at the time has the access to that shared resource. So but that using a synchronized keyword is not optimized because it's usually slow. It blocks the whole code. It blocks the whole portion of the code. So only for one thread have the access to it. So instead of using the collection, regular collection, and the synchronized keywords, so what we do is in Java we have also concurrent collection, right? Which is the thread safe collections. So for the map we are using, for example, here concurrent hash map, and for the list we are using copy on write array list. So if we run this, let's run this code and see that okay, for the key we have added whatever we want to add, right? So we have added key 0, key 2, 1, and so on. And for the list we have added again, we have added two item zeros because we are adding it twice, and the item ones, and so on. So what else we have, right, besides these two collections that we have just seen? So in the Java we also have for the map we have a concurrent skip list. For the set we have the similar thread safe collections for the queue, and for the list we have already seen. This is not the complete list, but it's the mainly used concurrent, mainly used thread safe collections in Java. But let's take a look how these thread safe collections work under the hood, right? So under the hood, what they do is they mainly rely on the CAS operations, compare and the swap. So they are also using a synchronize. They are actually using the synchronize in combination for the CAS, but mainly they are relying on the compare and swap operation. So let's take a look what is exactly compare and swap operation. So for that, let's take one simple example. So here what we do is we are creating atomic integer. It's the atomic integer. It's the way of it's a thread safe version of the integer, the same as we have the thread safe collections, and also we have a thread safe integer here, right? So we are creating here atomic integer, and we are creating two threads. And what each thread should do is we are calling a method. It should increment this value to atomic integer. It should increase that value to 5 times, and we are returning whatever results we are getting, right? So we are starting both threads. We are waiting until they are finishing their work, and then we are printing the final result, which should be 10 at this point. So what we do, the important part is what we do in the increment method, right? So in the increment method, what we do is, again, we are incrementing each of these threads for each of the thread, right? So we are incrementing the value of the atomic integer. We are incrementing that 5 times. But how exactly we are doing that? So here we are using the CAS algorithm. So what it does is, so first we are for the updated, we are setting that to false, and what we do is while the updated is not set to true, so we are doing the following operation. So what we do is we are reading the old value of the thread. So here, right, from the atomic integer, so whatever the old value, let's say that the old value, we're just starting out, right? So we are reading that old value is 0, so we are reading that zeros, and we need to increment that once, right? So in each operation, we need to increment once. So we are reading that value, and we are setting that the new value, whatever the value we want to update that to, right? And we are calling in the atomic integer, compare and set. We are calling the old value, and we are calling the new value. So with the old and new value, right? So if that succeeds, so which means that if this operation succeeds, compare and set, right, then in that case it will return updated. So which means that we are breaking that loop, and we are breaking that loop, so which means that we have updated that atomic integer once. If not, then we are doing that until we succeed. So let's take a closer look, right? Let's take with this example. So we have thread 1 and thread 2. So thread 1, so they are running at the same time, right? So thread 2 is running at the same time. So what we do is we are reading the value, old value, and both of them reads as 0. And then we are setting the new value. New value, we want to update that to 1, right? In both of these cases. So this one, right, it calls the compare and the set for 0 and 1, the thread 1. It succeeds because when it reads that value again, 0, and it sees that, okay, this is equals to the old value, it sets that to 1 and it returns true. But this one, right, the second one, it doesn't succeed. Because why it fails? Because when we are calling the compare and set, it reads the value, and it compares that value with the old value, and the value at this point is already 1, because this thread T1, right, it's already updated that, and this value is already 1, so it fails, it returns 0. Then it starts the operation again, then it goes. That's why we set that in the while loop. Then it reads that again. Now the old value is 1, and then it reads the new value. It wants to set to 2. It does it until it updates that value, right? It does that in loop until it updates that value. But another question is, when you look all of this, you may think about, okay, that's clear, but how about this part, right? How we make sure that this operation is, how about this part, right? How we make sure that this operation is atomic? Because here we are sending the old value and new value, and we rely that the compare and set will read that again and will set that value. We make sure that this operation is atomic because usually, right, most of the CPUs have the special instructions. Like, for example, we have the special operations just for the compare and exchange, right? So we make sure that this operation, actually, this will be atomic. So whenever we are reading the value, whenever we are reading the value again, so we make sure that that this operation will be atomic. So let's say that we are reading the value, and the value is at this point not, for example, in this case, right, the value is not 0 but 1. That means that another thread has already changed that value. Okay, let's run it and see that it works as expected. Let's run it, and as you can see here, first thread 0 increments the value, and the thread 1, and as a final result we get 10. So yeah, one more thing to add here. This operation, compare and swap, why it's preferred over the synchronize? Because it's called the optimistic lock. It doesn't block the whole operation. It relies on the loop, for example, in this case, on the while loop, in order to set that value. While in case of the synchronize, what we do is we are just blocking the whole, let's say that the whole block, or let's say that the whole method in some cases, just to make the update. So pessimistic lock, in case of in our cases, the synchronize, is much more slower than the optimistic lock, such as using the CAS algorithm here.